Article 250.122b of the National Electrical Code provides two different methods for sizing equipment grounding conductors. The first method involves using the circular mill area. The equipment grounding conductor shall not be less than the circular mill area of the ungrounded conductors. This method is based on the assumption that the equipment grounding conductor will carry fault currents that are equal to or greater than the phase currents. The second method involves using Table 250.122. The equipment grounding conductor shall be sized according to Table 250.122, which is based on the rating or setting of the overcurrent device protecting the circuit. This method is based on the assumption that the fault current will be limited by the overcurrent device. The conflict arises because Method 1 and Method 2 can result in different sizes for the equipment grounding conductor, even for the same circuit. This is due to the different assumptions used in each method. Method 1 assumes a worst-case scenario where the equipment grounding conductor will carry the full fault current. This typically results in a larger equipment grounding conductor size. Method 2 assumes that the fault current will be limited by the overcurrent device. This typically results in a smaller equipment grounding conductor size. In practice, disputes over equipment grounding conductor sizing can be resolved by considering the following factors. Firstly, the type of circuit. For circuits where the fault current is likely to be high, such as motor circuits, Method 1 may be more appropriate. Secondly, overcurrent protection. If the circuit is well protected by a low-setting overcurrent device, Method 2 may be acceptable. Thirdly, engineer's judgment. The final decision on equipment grounding conductor sizing should be made by a qualified electrical engineer with experience in fault current analysis. While there is a conflict in the National Electrical Code regarding the sizing of equipment grounding conductors, it is important to understand the assumptions behind each method and make an informed decision based on the specific circumstances of the circuit. Disagreements can be resolved through discussion, technical analysis, and consultation with qualified professionals. To elaborate further on the two methods, let's consider a practical example. Imagine a 20-amp circuit using number 12 American wire gauge copper conductors. Using Method 1, which bases the equipment grounding conductor size on the circular mill area of the ungrounded conductors, you would first need to determine the circular mill area of a number 12 American wire gauge copper conductor. A standard wire table will provide this information. Let's say it's approximately 6,530 circular mills. Therefore, the equipment grounding conductor would also need to be at least 6,530 circular mills, which corresponds to a number 12 American wire gauge copper conductor. Now, using Method 2, you would refer to Table 250.122 in the National Electrical Code. This table bases the equipment grounding conductor size on the rating of the overcurrent device protecting the circuit, in this case 20 amps. According to Table 250.122, a 20 amp overcurrent device requires a minimum number 12 American wire gauge copper equipment grounding conductor. In this particular example, both methods result in the same conductor size. However, in other scenarios, the results can differ significantly, especially with larger conductors or higher ampacity circuits. The critical difference lies in the underlying assumption. Method 1 prioritizes the fault current carrying capacity of the grounding conductor, ensuring it can handle a substantial fault current equal to the phase conductors. This is a conservative approach, suitable for situations where a high fault current is anticipated. Method 2, on the other hand, relies on the overcurrent device to quickly interrupt the fault current, thus allowing for a smaller grounding conductor. This approach is acceptable when the overcurrent protection is reliable and fast-acting. Now let's consider a more complex scenario involving a larger feeder circuit. Suppose you have a 400 amp feeder circuit using 500 kilo circular mill copper conductors. Using Method 1, you would need to determine the circular mill area of the 500 kilo circular mill conductors, which is obviously 500,000 circular mills. The equipment grounding conductor would also need to be at least 500,000 circular mills. This would require a very large equipment grounding conductor, potentially even larger than the phase conductors themselves. However, using method 2 and referring to table 250.122, a 400 amp overcurrent device typically requires a number 3 American wire gauge copper equipment grounding conductor. This is significantly smaller than what method 1 would dictate. In this case, the discrepancy between the two methods is substantial. The reason for this difference is that method 1 assumes a massive fault current potential requiring a large equipment grounding conductor to handle it safely. Method 2 assumes that the 400 amp overcurrent device will limit the fault current to a much lower level, making a smaller equipment grounding conductor adequate. The choice between these two methods depends on several factors. Firstly, the characteristics of the electrical system, including the available fault current and the impedance of the circuit. Secondly, the type and quality of the overcurrent protection devices. Thirdly, any specific requirements or recommendations from the equipment manufacturer. In situations where the available fault current is very high, or the overcurrent protection is not particularly fast-acting, method 1 may be the more prudent choice, providing a greater margin of safety. Conversely, in systems with well-coordinated overcurrent protection and lower fault current potential, method 2 may be acceptable, resulting in cost savings and easier installation. Ultimately, the decision rests on the engineer's judgment and a thorough understanding of the specific electrical system. A detailed fault current study can help determine the appropriate equipment grounding conductor size, ensuring both safety and compliance with the National Electrical Code. It's also important to consider any local amendments or interpretations of the National Electrical Code that may apply in a particular jurisdiction. These local rules can sometimes clarify or modify the requirements for equipment grounding conductors. Remember that the primary purpose of the equipment grounding conductor is to provide a low impedance path for fault current to return to the source, facilitating the quick tripping of the overcurrent device. This minimizes the duration of the fault and reduces the risk of electrical shock or fire. Therefore, selecting the appropriate equipment grounding conductor size is a critical aspect of electrical safety. Furthermore, it's essential to ensure that the equipment grounding conductor is properly installed and connected. All connections must be tight and secure to maintain a low impedance path. The equipment grounding conductor should be run along with the circuit conductors, and it should be sized appropriately for the entire length of the circuit. In summary, when sizing equipment grounding conductors according to National Electrical Code Article 250.122b, it's crucial to understand the two different methods and their underlying assumptions. Method 1, based on the circular Miller area of the ungrounded conductors, provides a conservative approach suitable for high fault current scenarios. Method 2, based on table 250.122 and the overcurrent device rating, offers a more economical option when the overcurrent protection is reliable. Resolving any disputes over equipment grounding conductor sizing requires careful consideration of the circuit characteristics, the overcurrent protection, and the engineer's judgment. Fault current study can provide valuable insights, and local amendments to the National Electrical Code should always be taken into account. By following these guidelines, you can ensure that your electrical systems are properly grounded and protected, minimizing the risk of electrical hazards. Additionally, remember that the National Electrical Code is updated regularly, so it's important to stay current with the latest edition and any applicable interpretations. Changes to the code can affect the requirements for equipment grounding conductors and other aspects of electrical safety. Continuing education and professional development are essential for electrical engineers and electricians to maintain their expertise and ensure compliance with the latest standards. Let's delve deeper into the factors that influence the selection of an equipment grounding conductor, focusing on the available fault current. The available fault current is the maximum current that could flow in the circuit under fault conditions. It depends on the source voltage, the impedance of the source, and the impedance of the circuit itself. A high available fault current means that a large amount of current could flow very quickly during a fault, potentially causing significant damage or injury. In situations with high available fault current, it's crucial to use a larger equipment grounding conductor to handle the current safely and ensure that the overcurrent device trips quickly. Method 1, which bases the equipment grounding conductor size on the circular mil area of the ungrounded conductors, is generally more suitable for high fault current scenarios. This method provides a greater margin of safety and ensures that the equipment grounding conductor can withstand the high current without overheating or melting. On the other hand, if the available fault current is relatively low, method 2, which uses stable 250.122, may be acceptable. However, it's still important to verify that the selected equipment grounding conductor is adequate to handle the expected fault current. A fault current study can help determine the available fault current and ensure that the equipment grounding conductor is properly sized. Another important factor to consider is the impedance of the circuit. Impedance is the opposition to the flow of alternating current. It includes resistance, inductance, and capacitance. A high impedance circuit will limit the fault current, while a low impedance circuit will allow a higher fault current to flow. In low impedance circuits, it's particularly important to use a larger equipment grounding conductor to handle the potential fault current. The length of the circuit also affects the impedance. Longer circuits have higher impedance, which can reduce the fault current. However, even in long circuits, it's still important to ensure that the equipment grounding conductor is adequately sized. The type of overcurrent device is another critical factor. Fuses and circuit breakers are the most common types of overcurrent devices. Fuses are generally faster acting than circuit breakers, but they need to be replaced after they trip. Circuit breakers can be reset, but they may take longer to trip. The speed of the overcurrent device affects the amount of time that the equipment grounding conductor needs to carry the fault current. Faster acting overcurrent devices allow for smaller equipment grounding conductors, while slower acting overcurrent devices require larger equipment grounding conductors. It's also important to consider the interrupting rating of the overcurrent device. The interrupting rating is the maximum fault current that the overcurrent device can safely interrupt. If the available fault current exceeds the interrupting rating of the overcurrent device may fail to interrupt the fault, potentially leading to a dangerous situation. In such cases, it's necessary to use overcurrent devices with high interrupting ratings or to use current-limiting devices to reduce the fault current. The equipment grounding conductor plays a crucial role in ensuring that the overcurrent device trips quickly and safely. A properly sized equipment grounding conductor provides a low impedance path for the fault current to return to the source, facilitating the tripping of the overcurrent device. In addition to sizing the equipment grounding conductor correctly, it's also important to ensure that it is properly installed and connected. All connections must be tight and secure to maintain a low impedance path. The equipment grounding conductor should be run along with the circuit conductors, and it should be sized appropriately for the entire length of the circuit. In summary, selecting the appropriate equipment grounding conductor size requires careful consideration of several factors, including the available fault current, the impedance of the circuit, the type of overcurrent device, and the interrupting rating of the overcurrent device. A fault current study can provide valuable insights and help ensure that the equipment grounding conductor is properly sized. Remember that the primary purpose of the equipment grounding conductor is to provide a low impedance path for fault current to return to the source, facilitating the quick tripping of the overcurrent device. This minimizes the duration of the fault and reduces the risk of electrical shock or fire. Also, you should refer to other sections of the National Electrical Code which relate to grounding and bonding, as well as any applicable local codes and regulations. These resources can provide additional guidance and clarification on the requirements for equipment grounding conductors. Finally, it's always a good idea to consult with a qualified electrical engineer or electrician when designing or installing electrical systems. These professionals have the expertise and experience to ensure that the systems are safe and compliant with all applicable codes and standards.